Thank you for the introduction, and I'm happy to be here and share our work on ACon scale adaptive conformal consensus for Provable blockchain oracles. This is in collaboration with Osbert, Bastani at UPenn and Taesoo at Georgia Tech. Blockchain itself may not be useful in isolation. It needs to interact with the environment. To that end, we need a sensor of the blockchain that measures the external activity of the environment, which is also called the Oracle smart contract. One example of Oracle smart contract is a price oracle. There is a market. It consists of usually two tokens, and it measures this ratio of these two tokens is changed over time through the external transactions. And there is price oracle that measures the ratio and estimates the price of, for example, Ethereum in USD. And this value is used in the downstream smart contracts. That means that the ratio can be, the attacker can issue a malicious transaction to distort this ratio severely, such that the price oracle could make a wrong estimate on the price of Ethereum, and that wrong value is propagated to the downstream smart contract. This is called the oracle manipulation. I want to highlight that this oracle manipulation is a really serious problem. I'll take an instance from the price oracle manipulation on DeFi protocol in Ethereum. In early 2020, there is a protocol called the BZX, and the attacker initialized the attack by conducting a price oracle manipulation and eventually get benefit from it about $1 million. And this kept happening over the time regularly. And this suggests that the price oracle manipulation should be rigorously addressed. And let's take a closer look at the price manipulation. This is the actual instant data from the inverse finance. And there are three markets, SushiSwap, Uniswap version 2, and the Coinbase, each of which measure the value of the coin called IMV. And the attacker conducted a price manipulation on the SushiSwap such that we can see the huge distortion on its value. But if you see the trend of the other market, the price of the other market, we can see there is some information that we can leverage and avoid this price of manipulation. One traditional mitigation of this price manipulation is mean of the multiple oracles. Here I visualize the mean value of the three price in solid black line. As we know, implementing mean is simple, so it is quite Ethereum friendly, and it is robust under the price manipulation. Its value is not affected. However, after that, the median value is affected for some reason, which may be fine, but it does not provide the anomaly signal for the other downstream smart contract. In short, median mitigation works but less informed, and we believe that the modeling uncertainty helps more informed decision. Key idea is we wish to leverage the uncertainty for consensus. Ideally, we want to measure the uncertainty of the price value such that this uncertainty closely predicts the price ranges. Under attack, still make a consensus, but after the attack, we could inform the anomaly signal producing the high uncertainty. Then how can you represent the uncertainty? We view Oracle smart contract as a prediction set model in machine learning. In particular, the market along with the price oracle, we consider that as a prediction set model where the input of the market is input of this model, and the output of it is the set of a prediction set, which is set of the price value instead of the point estimate of the price. For example, we can imagine the interval or value. Then here I want to highlight that the uncertainty is measured by the set size. So for example, model think the current situation is more uncertain than before, then it outputs a larger set, which means there are many other possibilities to be a true value. So this set size, larger set, could represent the more uncertain situation. Okay, then is this prediction set representation compatible to other application? Short answer is yes, and possible. Here, let's imagine this prediction set representation on the price. And the most famous application in DeFi is the loaning service. In this case, we can take the worst case price, in this case, the 1.5K, and just we can run the loaning service as it is without modifying anything. This shows that the prediction set representation may be compatible with existing ecosystem. Okay, then what could be potential challenges? First challenge is the learning uncertainty under natural shift over time. So as we know, the Ethereum price, for example, changes unexpectedly over time. Like its value is dramatically increased and decreased. To learn the uncertainty around this price value, we need to learn this base prediction set model, such that it can closely capture follow the trend along with the model the uncertainty. To that end, we use a known approach called adaptive conformal prediction. The details is in the paper, so please feel free, please check it out, our paper. Second challenge is learning uncertainty under adversarial manipulation. So as we know that the oracle manipulation distorts the price value, that means the prediction set model that learned on top of this value can be wrong, so it produces the wrong prediction set. To avoid this issue, we take a multiple measurement and construct a prediction set independently, and take a majority voting over this base prediction in intervals. For example, if there is 3 base prediction intervals set, and we can take a consensus over it and extract the consensus set like visualized in this case. Finally, this is the last but most importantly, we also prove that the correctness guarantee of our method and also produce the consensus set. In short, under some assumption, this guarantee means as follows. So our algorithm produces the consensus set over time, and the most of the case, assuming the alpha is very small, the true consensus value is included in the consensus set. That means we can trust this consensus set and also its measurement on the uncertainty. However, there are a few cases that it cannot contain the true consensus set, true consensus value, but it is controlled by the alpha, which can be arbitrarily small as long as we can feed enough number of data. And this proof provides us the trustworthiness on our algorithm and the constructed consensus set. Then how can we implement this ACon square algorithm in Ethereum? So this is the one way to implement it. So whenever a user wanna swap their coins, they call a swap function in the automated market maker, AMM. At the end of this code, we put the update function that updates the base prediction set. And this operation, and after this update, this function writes the prediction set in the block. And we have the same operation for all AMMs. If you want to make a compute the consensus set, then this another smart contract ACon square read this written prediction set over in the block and compute the consensus set in this way. And this is provided by some or other downstream application. Okay. Then we also evaluated our algorithm under natural shift. As can be seen, our method is visualized in the green and denoted by the ACon square. It's closely following this price changes nicely. And also we provided the empirical evaluation on the correctness of our theorem. I'm going to skip this explaining this, but please see our paper for details. Next, we also check out our algorithm under adversarial manipulation. So here, our algorithm is also visualized in the green area and also denoted by the ACon square. Under the price manipulation, it can still make a consensus. And we could see our algorithm output the larger consensus set, which means that it cannot make a consensus, but this signal can be used as alarm for the downstream application. Then, what could be potential limitation? One limitation is our theorem relies on the assumption called the identical label distribution, which is from the observation that if there is arbitrage, the price among the different markets is very well synchronized. However, this could be strong, so relaxing this assumption could be an interesting future direction. Another limitation could be a higher transaction fee for learning. So as I mentioned, for each AMM swap function, we have a machine learning module in it. At the time but this is expensive. At the time of when we are writing this paper, the gas transaction fee is about $31, which may be high. So that introduced us the interesting another question. Can you find an Ethereum-friendly learning algorithm? Okay, in summary, our proposed algorithm, ACon square, aim trustworthy Oracle smart contract backed by the machine learning theory. And we also shared our code, and feel free to play and check it. Thank you for listening.